Welcome back. We're going to start today talking about weather. So, we're going to talk about the variables that we use in weather for the most part in this lecture. Now, there are four factors that influence our weather. These four factors are the atmospheric moisture, what we term the humidity, and the temperature. Remember, the temperature is a measurement proportional to the kinetic energy of the molecules, the average kinetic energy. Then we have the air pressure, that is the force per unit area that's being applied on a surface. And finally, of course, the arrangement of land and water features makes a big difference to weather. So these are things that play into our weather. So let's look at these a little more carefully. So temperature, we've already studied temperature when we were in physics. We learned it was a measurement of the average kinetic energy of the molecules. So at high temperatures, the water molecules are moving fast, and so they bounce off of each other hard. And so it keeps them from sticking together. I have a picture coming up in a few slides. It's about 3 slides to show an illustration of that. So as temperature increases, you have less water molecules can stick together, so more evaporation. As temperature drops, then they're not hitting each other as hard. They can stick together, and then you have more condensation. So condensation is when water molecules stick together. And when condensation occurs, it actually causes the air temperature to drop, to cool. When evaporation occurs, I said that backward. When condensation occurs, let's just cover that later. I said it backward. I don't want to have to think about it too hard here. So condensation, when they clump together, evaporation, when they stay apart. Now we measure how much actual moisture is in the air, whether it's clumped together or not, with the humidity. So humidity is how much water you have divided by how much air you have. Typically it's in grams of water per kilograms of air. And humidity is not what you hear on the weather report. On the weather report, you hear them talk about the relative humidity. Relative humidity we'll talk about in just a minute. The relative humidity is the humidity divided by the saturation point. Saturation is what's the maximum humidity you could have. Now, hot air, because you have much stronger collisions because they're moving faster, you can have a lot more moisture in the air because it doesn't stick together as easily. Cold air can't have as much. So humidity is how much humidity, or relative humidity is what the humidity is, divided by what the humidity would be if we were right at that saturation point where we had as much moisture in the air as it could hold. Now, dew point, I went to a class on how to teach weather a few years ago before I started teaching physical science. So I would have some knowledge about that because that's the one area that I was weak on. And let's be honest, I'm still a little weak on it. But they said the dew point is really what we should pay attention to. Relative humidity, people get so confused. They say, it's 90% relative humidity. It must be very wet. Well, if it's minus 10 degrees and 90% relative humidity, it's actually quite dry because you can't have much moisture in the air at minus 10 degrees. Where if it's 90 degrees and 90% humidity, it's very moist. But the dew point is the temperature at which saturation occurs. That is the temperature at which you would have a relative humidity of 100%. And so the dew point tells you, it's a number that tells you how much moisture there is. If the dew point is 70 degrees, then it's, fairly moist. If the dew point is 90 degrees, then it's going to be, you have to raise temperature or lower the temperature to 90 for it to condense, that's really moist. If the dew point is minus 10 degrees, it's really, really dry. Now here's the picture I was talking about that illustrates the difference in high temperatures and low temperatures and moisture in the air. At high temperatures, they're coming and they're hitting each other hard and they bounce off. They can't stick together. At low temperatures, they're coming in a nice, slow temperature. They meet and apparently they kiss. Here's the calculation for relative humidity. I already mentioned the relative humidity is the humidity divided by the saturation humidity. So here it says water vapor content divided by water vapor capacity. Capacity means the saturation humidity. And then times 100%. So relative humidity is in percentage. Now, this graph illustrates the difference in temperature and humidity. So this line here, where it says evaporation rate equals condensation rate, that's the line of 100% humidity. If you're above 100% humidity, which you can theoretically do, you can have more moisture in the air than you can hold. We call that supersaturated. Any slight little disturbance will make it suddenly fall out. But when you're supersaturated, you're going to have more evaporation occurring than condensation. And so down here, you're supersaturated. Up here, you're unsaturated. That is, you can hold more moisture in the air. And the rate at which condenses is higher than the rate at which evaporates. So you can see you have the maximum specific humidity, the maximum amount of moisture that can be held in the air is a great function of temperature. So 40 degrees Celsius, that's around 100 degrees Fahrenheit. You have a very large amount of moisture in the air compared to that it can hold compared to at 0 degrees Celsius or 32 degrees Fahrenheit. In fact, if you compare those, that's about 5 compared to 50. So you can hold about 10 times more moisture in the air at 100 degrees Fahrenheit than you can at 32 degrees Fahrenheit. So 100% humidity at 100 degrees Fahrenheit is 10 times more moisture in the air than 100 degrees humidity at 32 degrees Fahrenheit. Here is the data for that graph just broken down into a table. And so you can see the actual number was 3.8 grams per kilogram at 32 degrees Fahrenheit. And this doesn't go up to 40 degrees Fahrenheit, but you see it at 30 or 40 degrees Celsius, or what I said was about 100 Fahrenheit. But you can see at 95, it's just a little under 10 times the humidity, or excuse me, the amount of moisture that the air can hold. So just to review some terms here, the dew point is the temperature at which saturation occurs. Condensation, that is water molecules sticking together to form droplets, occurs, it will occur when you're below the dew point, but you'll have massive condensation occurring when you reach the dew point. So you're going to have kind of some evaporation, some condensation at any temperature. But when you reach the dew point, if you go below the dew point, you're going to have massive condensation. If you go above the dew point, then you're going to have more evaporation than you have condensation. Well, if the water content is above the dew point. If the temperature is below, if the temperature is below the dew point, then you're going to have more condensation. If the temperature is above the dew point, you're going to have more evaporation. Water vapor condenses in the high atmosphere to form clouds. It can also condense at the low atmospheres, though, or low elevations. So don't take this to say water vapor only condenses at high atmosphere. It doesn't say only. It also condenses at low elevations, but then we call it fog or dew, or if it's frozen, frost. So the difference in fog and a cloud is altitude. My understanding is if it's within 50 feet of the ground, we call it a fog. If it's more than 50 feet above the surface of the ground, we call it a cloud, right? So there's no difference in what is a cloud and what is a fog, except for where it's located. Okay, so first question here, see if we understand what's been covered so far. As air temperature increases, as the air gets hotter, what happens to the relative humidity, assuming the moisture in the air stays constant? So this is for constant moisture in the air. Where if there's constant moisture in the air, a lot of people are going to say, well, that means the humidity remains constant, and they're going to be right. But that's not what our answers are. Humidity remains constant, but these are all relative humidity. That word relative means that we are actually looking at relative humidity is equal to the humidity over the saturation humidity. But saturation humidity increases with temperature. So as it gets hotter, that denominator increases. So if the numerator, the humidity is staying constant, but the denominator is increasing, then the relative humidity is going to decrease with temperature increase. So the relative humidity decreases. The bottom statement would have been correct if it didn't say relative. The humidity is unaffected, but the relative humidity does change because of temperature. Next question, when the dew point is high, what happens to the relative humidity? Well, the dew point temperature where relative humidity equals 100%. That is when the humidity equals the saturation humidity. So what happens when the dew point is high? What happens to relative humidity? Well, the relative humidity is unaffected by the dew point. Excuse me. Wait a minute. I looked at that wrong. I was thinking the other way. The dew point is unaffected by the relative humidity, but the relative humidity is equal to humidity again over the saturation humidity, and the dew point I just wrote up above is the temperature where the relative humidity is 100%. So the dew point, if the temperature goes up, the relative humidity goes down, just like we saw. And so when the dew point goes up, the relative humidity, that means you have more moisture in the air, and thus the relative humidity is also going to increase. Because the dew point going up means you're putting more moisture in the air so that it will condense at a higher temperature. And any temperature below the dew point, it will condense. So that was all talking about humidity and temperature. So now air pressure. Air pressure, the force per unit area caused by the air molecules. So if air molecules are moving faster, they're going to hit you harder and they're going to put more pressure on you. So as a general rule, higher temperature means higher air pressure. So that's what our statement right here is. Warm air exerts more pressure on its surroundings than cooler air. So when you have a warm front, the temperature is higher, but that means so is the pressure. So in the weather report, when they tell us about the atmospheric pressure, if the atmospheric pressure is high, then we say, oh, we have a warm front. If it goes low, we have a cold front. Now, here is a physics word. We go back to our physics, and when we learned about thermodynamics, we had this word adiabatic, which means that you cannot have any heat flow. And oftentimes people confuse heat with temperature. So we spent a lot of time in our physics section trying to make sure that we weren't confused about the difference between heat and temperature. So heat is energy passing in or out. And temperature will increase if heat travels in. Temperature will decrease if heat travels out. But we can have processes where there is no heat, but we still change the pressure. And if you change the pressure, if you compress something, you're putting energy in. So if you don't allow any heat to flow and you compress an object, like you have a tire pump and you compress the air in that pump, if you do it fast enough, no heat flows, but you put energy in so it gets hotter. So if you've ever used a hand pump to pump up a tire of a bicycle, you'll notice that hand pump gets hot because you're putting energy in, and you're putting energy in. It's somewhat adiabatic, that is, the heat can't flow out very quickly, and so the temperature increases. So this is something that's important when we talk about weather. So we talk about in weather things, parcels of air. So here we have a parcel of air. It's shown as a cloud, but that's just so we can observe it. It doesn't have to be a cloud. Well, if this parcel of air is warmer than the air around it, it will naturally float up. But as it floats up, if it is dry air, so I have here dry air. If it's dry, that is, if it doesn't have water droplets in it, then as it floats up and it expands, it will naturally cool. Expansion is the opposite of compression. Compression makes it hot, so expansion makes it cool. So it will cool by about 10 degrees Celsius per centimeter. Per centimeter, oh my, that would be quick. Per kilometer, per 1,000 meters, or 100,000 centimeters. So it will cool by about 10 degrees Celsius per kilometer. So as the air goes up, it's going to cool. Now, the air being hot makes it less dense, which is why it floats up. But as it cools, it will reach the point where it's in equilibrium with the air around it, and it will stop rising. So we call this the dry adiabatic lapse rate. If we have this parcel of air and it has no ability to transfer heat to the area surrounding, which actually makes sense. If you have this parcel of air, it can only transfer heat at its boundaries. And if the temperature outside is not very different, you're going to have very little heat transferring in or out as it rises. So it's pretty close to adiabatic. Now, that's one thing for air rising. This is occurring from natural convection. But our next picture here shows how a Chinook wind occurs. Now, I went to graduate school at Washington State University, and up there we had Chinook winds, named after the Chinook Indians. And the Chinook winds are warm, dry winds. And people used to talk about when those Chinooks come, you instantly feel the air temperature change. And if you are careful and want to, you can actually walk with your hands extended and have one hand in cold air and one hand in hot air. It's that different. And the Chinook winds are caused by having air forced over a mountain. We'll learn later about the word orographic. This is the orographic process. So you have warm, moist air that's being, I don't know why that should have, that's being forced to go up a hill. So you have to have a hill, and by hill we mean mountain. The picture looks like a hill, so I said hill. But you have warm air that's forced up a mountain. Well, as that warm air goes up the mountain, it's being forced to go to higher elevation. As it goes to higher elevation, it's going to naturally cool. But if that air was moist, it was close to condensation. If it cools, the amount of moisture it can hold drops, and so it becomes supersaturated. That is, it has more moisture than it can hold. And so then water droplets grow in size and fall out. So you have a lot of rain right here. So you might have heard there, like in Hawaii, it rains every day in the mountains. And it's because of warm, moist air being forced up over the mountain. And as it goes up the mountain, it cools and it drops out some moisture. Well, when the air gets over the mountain, it's now dry because it dropped its moisture and it comes back down. Well, if it comes back down, the air pressure around it increases, so it gets compressed. And as it gets compressed, it warms up, just like when we talked about pumping a bicycle tire up with the pump. So now you have a warm, dry air, and that's what the Chinook wind is. It's warm and dry. So this all started with something pushing the air up a mountain and then coming down the other side. And so this side here, when it's warm, dry, you don't have rain. So this side here is going to be an arid region. Arid, it's dry. And so you're likely to have desert type conditions out here. And in fact, that's how we have some of our deserts here in the United States, is because you have air that's forced up over a mountain, comes back down dry and hot, goes across a flat piece of land. It pulls up any moisture in the land because it's dry air. And so it makes desert. Now, we talked about the dry air lapse rate, the dry adiabatic lapse rate. That was if we had air that did not have water droplets in it. And it was about 10 degrees Celsius per kilometer rise. Now, if you have water droplets that form in that air, then we call it moist air. And condensation, so here, remember I said, let's just wait for later and make sure I get that straight. Condensation releases heat. So if you have water condensing, then it's going to raise the temperature. So instead of cooling by 10 degrees, you offset that 4 degrees per kilometer rise due to the condensation. So it's only 6 degrees Celsius for each kilometer. So if I have air that is dry and it goes up, then we have 10 degrees Celsius per kilometer drop. But if it's moist, I have the same action, but it's moist. Then I have 6 degrees Celsius per kilometer drop. And that difference in 4 degrees is because of heat released when the water condenses. And so that's the moist adiabatic lapse rate. Now, that's not the last of our lapse rate. The last of our lapse rates is the environmental lapse rate. This is the rate of cooling that generally occurs if you just go up in altitude. You don't have air rising or air dropping. You're just going up through stationary air. And that's a lapse rate of about 6.5 degrees Celsius per kilometer rise. So if we look here, if you have dry air, it's cooling faster than the environment. But if you have, I should have written that in something other than blue. So dry air, change and stay changed. It still won't change. There we go. Dry air is cooling faster than the environment. But the moist air is cooling slightly less than environment, because the environment was 6.5 degrees Celsius per kilometer drop in temperature. So what does that mean? Well, that has everything to do with how clouds and weather systems form. So in our next lecture, we're going to talk about cloud formation and whatnot. And these things will be important for that next lecture. But for now, we're just going to settle ourselves with, if you have rising air that stays warmer than the surrounding air, well, it's going to continue to rise because warmer air is less dense, and hence less dense things float on more dense. So continue to rise instead of coming back down. So we call that unstable air. So unstable air, we have this rising air because it's hot air. So hot air rises unstable. Eventually, as it goes up and it cools, remember that hot, dry air is cooling at 10 degrees Celsius per kilometer, whereas the air around it's only cooling at 6.5 degrees Celsius per kilometer. So you have about 3.5 degrees drop compared to the air around it as you go up. And so eventually you're going to reach the point where that rising air has the same temperature as its surroundings, and then it will reach equilibrium and just float there. And so it stops rising when you reach that equilibrium, but it doesn't sink back because it's in equilibrium. It has the same temperature, the same density as the air around it, so it just hangs out. Now, unstable rising air, that leads to cumulus type clouds. And we say a vertical development because it's rising, right? Rising, vertical development. Now, stable air forms stratus or layered clouds. So stratus clouds are layered clouds, horizontal layering, because you've reached stability. You're not rising, you're not falling, just spread out. Here is something, I grew up in California. I visited Southern California a number of times, but when I was in high school, we went down there on band tour to play at Disneyland. I realized just how bad the air was in Southern California. I mean, my lungs burned because we had a real smog problem back then. It's not as bad now because, thankfully, the Environmental Protection Agency has set regulations to decrease the amount of pollution. If you're paying attention worldwide right now, because of the coronavirus restrictions, people aren't driving, airplanes aren't flying, industry isn't operational. Bad for the economy, but really, really good for the environment. So air quality around the globe is really improving. Water quality around the globe is really improving because we humans really mess up our environment. And so with Los Angeles, the reason that it has such bad air pollution has to do with, well, first of all, we have that whole Chinook wind type thing. In the area there, we call them Santa Anas. But you have hot air that comes over desert. You actually have a situation. There's a desert here. You had, I don't know why that jumped. You had basically Chinook winds that came here, and then they go up over another mountain, and they come here. But you have the ocean. The ocean makes cool air. Now, normally hot air rises and cool air sinks, right? So if we have hot air up here and cooler air down below, we don't have the normal rise. This cool air is just going to be trapped. And so you put out pollution, and the pollution doesn't have anywhere to go. It can't rise up because you have the warm temperature above holding the cold air down. And so this temperature inversion basically traps this air. And so you just pollute that air and it doesn't dissipate. So I remember when I was in graduate school flying into Southern California to visit my family, and you would see mountains, mountainous regions. And in those mountainous regions, you saw smog filling in. Like, oh my goodness, that's disgusting. It really is disgusting because you have the warm layer up here and the cool air down here trapping in all that pollution. It's just terrible. So that's an inversion layer, temperature inversion that traps the pollutants in there. It also has some cool features like mirages. A normal mirage you see when you're driving down the road, you look at the road and you see what looks like water on the road, and you're actually seeing, here's the road. You have the blue sky up here, and the light comes down and not hits the road, but bends back up due to refraction, and you see a mirage. You're actually seeing the sky in that mirage. But with this inversion layer, you have the opposite thing. So if you're here in Los Angeles, you might look up here, and because that inversion layer, the light reverses, so you see the ocean up in the sky. So that's also a kind of mirage that occurs because of the temperature inversion. Okay, so we actually have reached the end of the lecture. I just have one last question here before we go with our weather variables. What does the image below demonstrate? And what we're looking at specifically is this. You might recognize this is the Golden Gate Bridge. Obviously, the Golden Gate Bridge is not a golden color, it's a red color. They paint it regularly to keep that color. I believe they're constantly painting. They start at one side, go to the other, and come back. And you have in the background San Francisco. Something that I think is very cool is this. This picture was obviously taken with the intent to frame the Transamerica building, this thing right here, the Transamerica building. It's a very unique, pretty building in my opinion. I've been up to the observation deck in there. I've also eaten at the restaurant at the top of this building. I like the city. They call it the city, by the way. So the question is, what does the image below demonstrate? So I know there are clouds in the background here. We'll talk about those in our next lecture. But this right here, what is that? Well, the answer is that's a fog. What is a fog? It's water condensation below 50 feet. And so that's illustrating condensation. All right, hope this lecture gave you some good insights. The next lecture, we'll talk about how this can then help us to understand a little bit about weather. Have a great day.